Hi everyone, in this video we're going to continue solving trig functions with some quadratic structure. This one has a typo, so add a 3 in there if you've printed this off. Okay, so this one does have some trickiness going on, but I didn't intend for it to be that. When you have two different angles in your trig function, so one's a p and one's a 3p, for example, that's pretty tricky, and we will find ways to deal with that in some situations, but that's not what I'm planning on doing here. The other thing that can be tricky is when you have more than one trig function, so we will want to tackle that one here. Okay, so I have a sine of 3p and a cosine squared of 3p. If I ideally want to get down to a single trig function, and sometimes you can't do it, so you could try things like factoring to separate the two different trig functions, but here I can. I can say that cosine squared theta, cosine squared 3p in this case, is the same as 1 minus sine squared 3p. So this isn't anything dependent on what the equation is saying. This is something that is always true. This is our Pythagorean identity. Sine squared of an angle plus cosine squared of the same angle always give you 1. So if you take 1 and you subtract sine squared of the angle, you should get cosine squared of the angle. So that's going to be my very first step. I'm going to say I have sine of 3p and 2 times 1 minus sine squared 3p, and that equals 1. So sine of 3p plus 2 minus 2 sine squared 3p equals 1. Okay, so this is looking a little bit better. Before I get very much further, I think I want to look for my next big goal. Because I see this quadratic structure, I'm thinking about the tricks that I have for solving quadratics. So that would be things like factoring, square rooting both sides, using the quadratic formula. So this one's definitely not set up to square root, because if I isolate the sine squared and try and take the root, there'll be a sine on the other side that'll get trapped under the root. So that's not helpful, which means I either want to factor or use the quadratic formula. So it needs to be set equal to 0. Both of those methods would require that. So I'm going to go ahead and move everything right. You get to choose. I like to choose so that this sine squared ends up with a positive coefficient. So I'm going to add 2 sine squared 3p to both sides. I am going to subtract sine 3p from both sides. And I'm going to subtract 2 from both sides. Since I already have a 1 here, that will become negative 1. Okay, so I'd always try factoring. And if I get stuck, I can use the quadratic formula. So for this one, if I have a 2 sine squared 3p, I don't have a lot of choices. I need to split that up into a 2 sine 3p and a sine 3p. And then my last is a 1, so I have to use a 1 and a 1. And I get to make one of them positive and one of them negative. So if we look at, we've already built this so that our first is good. First gives us the 2 sine squared 3p. Our last is good. It gives us the 1, and we're about to deal with the sine. We're worried about the outside plus inside giving us negative sine 3p. So my outside is 2 sine 3p. My inside is 1 sine 3p. If I'm going to make one of those two negative, it should be the outside, so that it is a negative 2 sine p plus sine p, which will give me my negative sine p, 3p. Okay. So I've got it factored and equal to 0, which means I can now split it up and take each factor, oops, I'm getting ahead of myself, plus 1, there we go, equals 0, and set it equal to 0, or okay. Which means in this first equation, I'm going to do 2 steps here since I'm hitting the bottom of my space. I could subtract 1, this is supposed to be a plus, so I could subtract 1 and then divide by 2, which would give me sine 3p equals negative 1/2. And in the second one, I can add 1, so sine of 3p equals 1. And those statements are both ready for the unit circle. So if I go up to my unit circle and I say sine 3p equals negative 1/2 means y is negative 1/2. So that's going to put me at a negative pi over 6 or a 7 pi over 6. And as always, there's infinitely many different arc lengths we could choose, but I'm just picking one to kind of identify my points. And then I'm also interested in when sine of 3p equals 1. So here's where sine equals 1. And basically what we're doing here is solving for what do you have to plug into sine to get out a negative 1/2 or a 1. So you do want to be kind of aware that what we're really solving for is 3p. So we're solving for the input of sine, which means that 3p could be any arc length that lands at any of these points. And if we want to find p, we'll have to divide by 3. So okay, so let's do solutions. So this would be like the part A from your homework. Solutions on 0 to 2 pi. So just the solutions that you hit in your first lap around. So starting from here, if I head around the unit circle, my angle increases, and the first point that I hit that's one of my solutions is this one, and the arc length that gets me there is the pi over 2 that I have written down. So this is 3p equals pi over 2, which means p equals pi over 6. And then as I continue, the next one I hit is 7 pi over 6. So 3p equals 7 pi over 6, which means p is going to equal 7 pi over 18. And then as I continue, the next one I hit, so I said that the arc length was negative pi over 6, and that is one of them, but that's not the one that we're getting. We've gone almost all the way around, so that is 11 pi over 6. Uh, 11 pi over 18. And it's really tempting to say, oh, well, I'm done. I made it all the way around the circle. But this is actually a little tricky. Once again, you have to be careful. We have made it all the way around the circle for 3p, but we want to know what values of p are between 0 and 2 pi. So right now we've made 3p be between 0 and 2 pi. So we very likely have not caught all of them. We've got this pi over 6, this 7 pi over 18, this 11 pi over 18. This isn't even halfway around the circle yet. 18 pi over 18 would be halfway around. So we're not done. What I would say, this one's particularly messy and that it has a lot of answers, is that in this case, the part B might be kind of helpful. So if we try and build up the part B, which is all solutions, I would look at this and say, well, I need to figure out how the spacing works. Can I mush any of these together? So I don't see any that are straight across, but I do see that this is a pi over 2 plus pi over 6, which is what, 3 pi over 6 plus another one, 4 pi over 6. So this distance is 2 pi over 3. 4 pi over 6 reduces to 2 pi over 3. If we look right here, we can do that same process, or we can just recognize that there's some symmetry here. This is also 2 pi over 3. That's the exact same arc length in a different position. And then this one is 7 pi over 6 to 11 pi over 6. So 7, 8, 9, 10, 11. That's 4 pi over 6s, which is also a 2 pi over 3. So I can actually describe all three of those, the arc lengths that land at all three of those points with a single statement. I can say x, p, 3p even. Wow, let me catch back up with my problem. So the arc lengths on this unit circle that I've drawn could be pi over 2 plus 2 pi over 3k. And again, you can choose any one of the three and any arc length that lands at any one of the three as your starting point. The spacing's really key, but the starting point you get to choose. Okay, so we do have the same problem as above in that this is the value of 3p and we want p, but this one's really nice because not only does it push that first solution back to pi over 6, it also tells us how far apart they're going to be after that. So 2 pi over 9 is what we get. So that would be my answer to part B. And I can actually use that to build up some of the solutions for part A. So I would say this is going to be easiest if I get a common denominator here. So 18, I'm going to say I have multiply top and bottom by 3. 3 pi over 18 plus 2, no, 2, I'm multiplying by 2, so 4 pi over 18k. So the k's, let's see, so k equals 0 gives me 3 pi over 18, which is my pi over 6. You can check, sometimes you might need to backtrack a little. So for example, if I let k equal -1, I get 3 pi over 18 minus 4 pi over 18 plus a negative 4 pi over 18. So that's negative pi over 18, which means it's not a good solution for A. I don't want negative solutions. So it really is good in this case for us to start with k equals 0. But say we had not used pi over 2 as our starting point, we'd used 11 pi over 6. We might have to use some negative k's and positive k's. And then you should just be able to walk through this. So if I go 3 pi over 18 plus 4 pi over 18, I get 7 pi over 18, which was the next one on my list. So that looks good. That was k equals 1. If I do 3 pi over 18 plus 4 pi over 18 and k equals 2, so I get 3 plus 8 is 11 pi over 18, so that looks good. For k equals, what was this? I'm going to write them down. This is k equals 0, 1, 2. So for k equals 3, I have 3 plus 12 pi over 18, so 15 pi over 18. When k equals, where am I? That was 2, 3. When k equals 4, it's 16 pi over 18 plus 3, 17, 18, 19 pi over 18. And this gets to be kind of a long list, but I want to talk through a little more. I want you to notice over here that the space between your solutions, what's happening here is we go up by 4 pi over 18 every time, which is exactly what I would expect because that's what this notation means. It means your solution should be 4 pi over 18 apart. So we can just continue adding 4 pi over 18s. So I have a mess here already. I'm going to quit writing, but I would say we'll have 23 pi over 18, and then we'll have 27 pi over 18, and then we'll have 31 pi over 18, and then we'll have 35 pi over 18, and that should be the last one. And the way I know that is that if we're talking about pi over 18s, 18 pi over 18 is pi, 36 pi over 18 is 2 pi, and we were supposed to stop before we hit 2 pi. So 36 pi over 18 is our stopping point, and we got to 35 pi over 18, and anything after that would be too big. So I don't think I was mean to you on your homework. I don't think I gave you one where you have like 12 solutions to list or whatever beast of a number this one comes up with, but that would be the process. If it starts to get a little bit more tedious, you can always just go to your all solutions notation and pick different k values. Okay, so let's look at number 10. I'm going to copy it down since I used up half my room. Solve 2 cosine gamma equals sine squared gamma. Okay, so on any of these, if you are feeling comfortable, I highly recommend at this point going ahead and pausing and working on this thing and then coming back and checking in. So this one, the beginning is very similar. I don't really like that I have 2 different trig functions. The one that's easy to switch is the one with the second power. So really avoid the temptation to say that cosine gamma is 1 minus sine gamma. That is not true. It only works if you have the squares. It only works if you're doing the Pythagorean theorem thing. And then I'm going to move everything to the left. I'm going to set it equal to 0. So I'm going to add cosine squared. I'm going to add 2 cosine gamma, and I'm going to subtract 1. Okay, so let's see. Like I said, would always try and factor. For this one, if I'm going to split up a cosine squared, it's going to be into a cosine gamma and a cosine gamma. The 1 has to be a 1 and a 1. I don't want to get into fractions. So my choices are now, should this be a plus and a minus or a minus and a plus? And if you notice, everything else about these factors is identical. So it shouldn't matter. I should get the same thing no matter which order I choose. So if I'm checking myself, the first is cosine squared. That looks great. The last is -1. That looks great. The outside is a negative cosine x, and the inside is a positive cosine x. So when we add that up, we're going to get 0, which does not match up with our 2 cosine gamma. So this is not good, and I can't really see any other options. So I'm going to say I think this is not factorable, which leaves me with square roots or quadratic formula. This is not set up for square roots. If I isolated the cosine squared and did a square root, I would have cosines under that square root. That's bad. So I'm going to go for my quadratic formula, and I'm going to say, okay, well, it looks like I have an a value of 1, a b value of 2, and a c value of -1. So I'm going to get opposite of b, -2, plus or minus the square root of b squared, which will be 4, minus 4 times a, which is 1, times c, which is -1. So it ends up being minus a -4, which is a +4. Okay, what is really important to realize, everything I just did was great, but normally we would say, okay, I've got ax squared plus bx plus c equals 0, so I use a quadratic formula and it tells me that x equals all of this. Right now what I'm doing is I'm saying I have cosine gamma squared plus 2 cosine gamma minus 1, so the x part of that is the entire cosine of gamma. You can't just pull the gamma out of that, that would be wrong. So let's see. I'm actually going to simplify this one a little bit. It does simplify nicely. It's okay if you don't, but it'll make this a little less messy to deal with. So that's a root 8. 8 can be split up into a 4 times 2, and it's always legal to split square roots over multiplication. So the square root of 4 is a 2. So I have cosine of gamma equals -2 plus or minus 2 root 2 over 2. A lot of 2's in this one. And I can split that up. And I get to do some really nice canceling. So it looks like I'm going to get cosine of gamma is equal to -1 plus or minus the square root of 2. Okay, so that gives me 2 statements that are both ready for the unit circle. So I have cosine of gamma, and then I'm just going to split them off. Could be -1 plus the square root of 2 or -1 minus the square root of 2. And I'm fine with the exact answers at this point. But just in terms of trying to figure out where to draw this on my unit circle, I am going to get a decimal approximation. So the first one was -1 plus the square root of 2, which is about 0.41. And then if I do -1 minus the square root of 2, I get about -2.41. Okay, so decimal approximation is fine so that I know what I'm talking about here. So the first one says my x-coordinate is roughly 0.41. Or we could say x is exactly equal to 1 plus root 2. Okay, so that gives me a point in quadrant 1 or quadrant 4. The other one is saying that my x-coordinate is -2.41. So if you haven't noticed already, I hope that you notice now that the smallest x-coordinate I can get on the unit circle is -1, which means this is impossible. So actually I get to cross this one out altogether. It's really just the first one I'm worried about. So I'm down to cosine gamma equals -1 plus root 2. in order to get my solutions, I'm going to have to use a calculator for this one. I'm going to use inverse cosine. I certainly don't recognize -1 plus root 2 as a special value. Okay, so inverse cosine of -1 plus root 2 is approximately 1.14. So that gives me this arc length. I want both of them. So my inclination would be to just say plus or minus 1.14. And depending on your directions, that's great. But I want to be a little careful here. Let's do it like we'll see on the homework. So for your part A, the question will be what arc lengths between 0 and 2 pi? So I'm good with the 1.14. That is bigger than 0 and smaller than 6.28. I'm not good with a -1.14. That's smaller than 0. So I actually need to say, okay, if I start standard position, start at 1, 0, start with positive angles. In my first lap around the circle, which arc length will get me to that bottom point? So this is 2 pi minus 1.14. So for that, on 0 to 2 pi, it would be, so this one's a little picky. There's only one correct arc length that you can use to answer part A for these points. You do not have your pick of the infinitely many arc lengths that land there. You only get the one that's between 0 and 2 pi. And then for B, I'm going to go ahead with my plus or minus because while this doesn't truly make it a single statement, it surely makes it a lot more concise, easy to look at. So I'm going to say I could either start at 1.14 and then stop every 2 pi before and after that, or I could start at -1.14 and stop every 2 pi before and after that, which looks like this, where k is an integer. Okay. So that was number 10. Let's look at number 11. Okay, so again, if you're feeling comfortable, absolutely you can pause these and give them a try on your own. There's nothing too big sneaking in here. So for this one, in fact, thinking back to this one, I know for sure that nothing too weird happens in this. So it's a great one for you to practice. Okay, talking and I'm not saying what I'm thinking here. What I'm thinking is it's quadratic. The only trig function I see is the sine. So I'm just going to go straight for trying to solve the quadratic part. So I don't want to use a square root since I have sine squareds and sines floating around, which means either quadratic formula or factor, which means set it equal to 0. Okay, so I'm going to try the factoring. If I want to split up a 3 sine squared k, I'm going to make it a 3 sine k and a sine k. If I want to split up a 2, I'm going to make it a 1 and a 2. So I need to start thinking about this. Okay, so if I go, let's see, if I go 2 and 1, then I would get a 3 sine k for my outside and a 2 sine k for my inside, which is really tempting because 2 and 3 will add up to 5. But I don't get to add. One of them has to be negative, so I need the difference to be 5. So I'm thinking I am actually going to want to flip-flop that and make it 6 and 1. So if I have a positive 6 and a negative 1 times my side k's, that will add up to 5. So I've got it factored and equal to 0. Which means I'm ready to set each factor equal to 0. And this one I can solve by adding 1 and then dividing by 3. The other one I can solve by subtracting 2. Okay, so now I'm unit circle ready. So I know that my y is either 1/3 or -2, which is way down here, so I can actually throw that away. That's impossible. I can't be -2. So now I just need to find an arc length that lands at one of those. Since 1/3 is not a special value, that becomes a calculator question. So just think carefully about this. You can use your calculator if it's not a special value. if it is a special value, so if this was y equals 1/2 or 1 over root 2 or root 3 over 2, I would expect an exact answer. I'll try and be really clear about that on test, but I want you thinking about it before then. Okay, so this tells me that this little positive arc length is about 0.34. So if I want all solutions from 0 to 2 pi, that's the first one. What was my variable? K is about 0.34. The other one, there will only be 2, needs to be this distance. That's the only arc length that's positive and smaller than 2 pi that lands at this point. I could do a negative one, but that doesn't fit my domain restriction. I could go all the way around, also doesn't fit my domain restriction. And that one, we can use symmetry across the y-axis, so I know this distance right here is also 0.34, which means the arc length I'm looking for is pi minus 0.34. Okay, so there's the solutions between 0 and 2 pi. If I instead want all possible solutions, there's no nice way to do this one. Well, there's one, but I don't really want to mess with it. It is possible. Ooh, don't take that as a solution. It is possible to say, well, if I start at the top at pi over 2, I can go plus or minus whatever that is, pi over 2 minus 0.34, and get both of them, but I don't need you to get that creative. I'd love it if you spotted the symmetry over x-axis as plus minus, but this one I would just say k is approximately 0.34 plus 2 pi. I don't want to use k again because that's all my variable already, so I'm just going to use n's this time. I don't want to force k to be an integer if it's my variable. Or k could be pi minus 0.34 plus 2 pi n, where n is an integer. So feel free to use k's or n's or whatever, but do make sure that that variable that you're using to represent the integer multiples of your space is not the same variable you're solving for. All right, sorry, super long one. Thank you for watching.